Okay, so let's do some examples that utilize the three heat equations that we have. So here's an example. We have a certain amount of a compound, 0.126 moles, that we dissolve in a calorimeter. Now, those dissolution processes that we've talked about throughout the semester, they either generate or take in heat. So they're either exothermic or endothermic. And we can quantify that with a delta H of dissolution, right? So we're describing the chemical reaction with a delta H. So we dissolve it in a calorimeter and we're given a C cal. So we're given information about how that calorimeter deals with heat as you see changes in temperature. If a delta T of minus 2.50 degrees Celsius observed, what is delta H for this dissolution? Okay, so a couple things that kind of help us organize our thoughts with how we attack this problem. All right, we're given a C cal. So we know we have three different Q equations, but as soon as we see, all right, some indication that we're given one of our three different C's, then we know we can write one of our three different equations. And from our last discussion, we know that when we're dealing with, okay, a calorimeter, as soon as you see a calorimeter constant, the one heat capacity formula that we have is Q equals C cal, excuse me, Q equals C cal delta T. Now we also know that when we're dealing with a calorimeter, we're dealing with a heat exchange. So we also know that Q lost equals Q gained. So I'm going to go over this one more time. All right. We look for indications about which Q equation to use. And if I see the calorimeter constant, I know that Q is equal to C cal delta T. That's the one Q equation that had a C cal in it. I also know that I'm talking about a heat exchange here. I'm running a reaction in a calorimeter. Two different things are mentioned. Reaction in a calorimeter. So then I have to write minus Q lost equals Q gained. Right. Now what I like to do is I like to take the extra step and think about what's losing heat and what's gaining heat. Okay. So minus Q, I mean, it doesn't really matter as long as the negative sign is on one side. But essentially if I look at this, okay, the calorimeter is losing heat because the temperature is going down. All right. What's gaining that heat? The reaction that we're running. We're running a dissolution reaction. Okay. Now, we need to organize our thoughts one more step before, all right, we can go on and try to tackle this problem. We want a delta H. Well, for us, delta H's are Q. And if we think about the units of delta H that we're going to get here, right? Do you remember how delta H was presented to you when it was a delta H of combustion? It was given to you in terms of kilojoules per mole of the thing that we're referencing. And that's exactly the same thing with this. Any process that's referencing a component of a reaction, so this compound, right? We want to know its delta H of dissolution. What we look for is energy information, and we divide by the number of moles. Okay? So whenever you're asked to calculate a delta H, Chem 101, your book, me, we're going to want you to take the kilojoules and divide it by the moles. Right? So then how are we going to figure out the kilojoules? Okay? These kilojoules come from the reaction energy. Right? So we need to be careful. We want to know if we're referring to this reaction, how much energy is associated with that reaction per mole of substance dissolved. Okay? So if I can use this heat exchange formula, knowing that Q cal is equal to C cal delta T, then I'm given the number of moles, and I have everything I need to put it together and take the energy of the process, divide by the moles that I'm given, and that is your enthalpy for the process. Okay? So that's our thought process to actually sort of start this problem. So let's take the information that we have and let's make sure we can get everything in the correct spot to get the correct answer here. All right. We already know moles, so that part's done. So the rest is just how do we get how do we get these kilojoules out? How do we get the energy information out? Well, all right. Q for the reaction, which is going to go in the top here, right, is equal to minus Q for my calorimeter. And as we said before, we remember the minus sign, but Q for the calorimeter is equal to C cal delta T. Look at the information that's given, right? C cal is given as 1.1 kilojoules per degree Celsius. Your delta T is given as minus 2.50 degrees Celsius, right? Now this could be Kelvin, because remember delta T's, they're the same in degrees Celsius or Kelvin, but this is a nice example where we see that, okay, we can cancel that. But even if this was Kelvin, it would cancel here, because remember delta T's in degrees Celsius are the same as delta T's in Kelvin. So I plug this information, all right, into my calculator, and what I get is 2.75 kilojoules of energy. The negative and the negative cancel each other out. 2.75 kilojoules of energy with two significant figures are associated with dissolving 0.126 moles of this compound. Now we can take this and put it in the numerator, right? Also, before we get there, 1 second, does this sign make sense? Notice we have a positive sign, right? Our delta H then is going to be positive, which means we have an endothermic process. Does that make sense? Well, yeah, because inside that calorimeter, you saw its temperature go down, okay? So where did that energy go? It was gained by the process that was enacted, the dissolution. So always kind of take a second to make sense of your sign, because a sign error is just one easy thing that could happen here where you lose points where you don't really need to. Just always take a breath in these problems and say, hey, does it make sense that this was endothermic? Well, yeah, I put it in something that was warm and the temperature went down, all right? So it sucked energy into itself, right? An endothermic process. So now let's finish this problem. Let's take our kilojoules of energy that we've calculated, right? 2.75 kilojoules. And then let's divide by the 0.126 moles of compound. And that's what we're always going to use as a delta H. We'll look for energy and divide by moles, right? And so when we do this and then round to the correct number of significant figures, because there's only going to be two significant figures, right? What I get is 220, right, kilojoules per mole, right? 220 kilojoules per mole. As always, please check my work. But that's how we can use a calorimeter, right, to get at a delta H. And now this delta H we could turn into a thermochemical delta H. We could write it aside a reaction, and we could build our mole-to-mole bridges from there, right? So this is how we use this experimental technique of calorimetry to get at really important information. Let's do a few other examples together, because it's not the easiest, especially the first time you're seeing something like this. And you might not have seen this sort of thing in high school. It might be one of the things in chemistry where you haven't really had a lot of experience with yet, okay? So it's worth us doing a bunch of examples together. So let's look at the examples on your slideshow. So if you look at slideshow for chapter 5, but you're going to look at slide 4. Right. You'll see a couple examples there, okay? We're going to go through a few of these. And the first example that we're going to do is the bullet point at the top that deals with a chunk of silver, right? And so for this first problem, right, what you're given is a specific heat capacity for silver. And you're given that it has a specific heat capacity of 0.24 joules per gram degrees Celsius, okay? You're given a mass of silver. That's 150.0, right, grams. You're given a final temperature in Kelvin, which is 298.15 Kelvin, and you're given an initial temperature of 273.15 Kelvin. Now what you're asked is, hey, if I want to see this change in temperature, if I want to start at this temperature and go to this temperature, right, how much energy is required? Now, one thing I want to point out about this starting point is notice how there's only one thing mentioned. It's not like we're saying, hey, we're putting this silver in a calorimeter, or hey, we're nestling this silver up against something else. There's only one thing mentioned. So actually this problem is a little bit easier than our last example because when there's one thing mentioned, the only thing you have to consider is a Q equation. You don't do minus Q lost equals Q gained. You can just jump right to the Q equation. Well, what Q equation am I going to use here? Remember, it all depends on the type of C that you're given. So what we're going to calculate here, right, is based off of, okay, yeah, when there's a grams down here, I'm going to use the equation that's Q equals MC delta T. And I don't have to worry about minus Q lost equals Q gained because there's only one thing mentioned. So just using this formula, right, will get me everything that I need. So Q is our unknown, so we better know everything else on the right-hand side. 150.0 grams, right, is our mass. Our C is 0.24 joules per gram degrees Celsius. And remember, T final minus T initial is our delta T. Okay. So if I look at this delta T, right, it looks like a 25 Kelvin delta T. So I write this as 150.0 grams, 0.24 joules per gram degree Celsius. And then this looks like 5.00 Kelvin, right, for my delta T. Oh, sorry, not 5, 25. Okay, so now you might be running into an issue, except I've stressed this a couple times now. So you might say, hold on a second, I have degrees Celsius here, I have Kelvin here, I better change those to make sure they cancel out. Remember, this delta T came from measurements in Kelvin, but a delta T in Kelvin is the same as a delta T in degrees Celsius. So long as you're using a delta T, at the end of a delta T process, if it's more convenient for you to just say, hey, that's actually degrees Celsius, because you understand the markings on the Kelvin thermometer are the same as the markings on a degrees Celsius thermometer in terms of their spacing, then you can do so that the units then cancel correctly. And what we'll be left with is a Q that we can go ahead and calculate. And a Q is a heat and a Q is an energy. So we're answering for energy by calculating our Q. There'll be two significant figures, and what we get is 9.0 times 10 squared joules. Right, 9.0 times 10 squared joules. Does it make sense that this Q is positive? What did the temperature of our silver do? It went up. What's the only way its temperature can go up? If it gains energy, right? If it gains energy in the form of heat. So yeah, it does make sense that this was positive, okay? So the second bullet point under silver then says, hey, we're going to change up some things here, except the heat capacity of silver doesn't change, okay? It belongs to silver, so we can use it again, we can use it again for this problem, all right, the second bullet point down there. Now for this second bullet point, what it tells us is, hey, we observe 1.25 kilojoules of energy affecting the silver. And when we do that, we see a delta T of 3.2 Kelvin. So now they're not giving you initial temperature and final temperature, and Chem 101 will do this too, all right? Sometimes they'll give an initial temperature, final temperature, and sometimes they just straight up give you delta T, right? They give you delta T is 3.2 Kelvin, and now what they asked for is the mass. Well, remember, if this is a delta T, we could call this 3.2 degrees Celsius as well. Notice again, I just want to go over the identification. It's not saying anything about a calorimeter. It's not saying anything about any other object. It's saying focus down just on silver. Just silver by itself. Okay? And with just a focus on silver by itself, right, what that tells us is that we just need one of our Q equations. Well, what Q equation are we going to use? Again, we see grams down here. So Q equals MC delta T. Let's think about the information we have this time. We have 1.25 kilojoules of energy. Our mass is our unknown, right? We do have 0.24 joules per gram degree Celsius as our C, and we're also given a delta T as 3.2 degrees Celsius. So we do have everything we need to solve this problem except for mass. And that's the unknown that we're trying to solve for. So actually, we're really happy with our setup. Okay. I want to point out one thing again before we start. Notice that this is a positive value. And what is our delta T? Our delta T is also positive. So it was another situation where we heated this up. It gained energy and its temperature went up. Okay. Now, I see one issue here to start with, and I'm going to point this out because it happens a bunch, right? We're going to eventually try to solve this mathematically, but, right, notice that there are kilojoules here and there are joules there. We still have to pay attention to units, right? Kilojoules on this side of the equation will not cancel with joules on that side of the equation, okay? But if I take this kilojoules and I turn it into joules, and we know how to do that, right? And I write this as 1250 joules, because essentially, in case you don't remember, 1 kilojoule is 1,000 joules. If I use this conversion factor there, I can turn this into 1250 joules with 3 significant figures, right? I still have my mass here. I have 0.24 joules per gram degrees Celsius, and I have 3.2 degrees Celsius. My degrees Celsius will cancel. I have a joules here and a joules here. Those will actually cancel as well. Okay, and if you follow through with the mathematics, right, I have a per gram here, but what's going to happen? Let's solve for M. So M looks like our 1250, and its joules are gone because it cancel with these, right? I'm going to take this fraction here and invert it, okay? So I'm going to put a 0.24 here. But what happens to the grams when I invert this to bring it to the other side? Grams goes up in the denominator, okay? So my mass is going to have units of grams, and that's exactly what we need. That's a good unit for mass, all right? What happens to this 3.2? You would divide by it, all right? So now you could do this step by step, but all I'm showing you is that you need to pay attention to units here. The joules and the joules cancel, degrees Celsius and degrees Celsius cancel. The grams comes over to be the numerator on the opposite side, and that's actually exactly what we want. Our answer will have 2 significant figures. 1.6 times 10 to the third grams of silver is the answer when you enact this mathematics. That's the same as 1.6 kilograms of silver. So when you do a problem in Chem 101, just make sure you pay attention to units, okay? So again, for these simple problems, these simple starting problems, I kind of notice that we're looking out for whether heat exchange is occurring or whether it's not, okay? And if it's not, like this silver example that we did, right, then we just need a Q equation and we can analyze from there, paying attention, as always, to units and significant figures, okay? So I'm going to do one more example, but I'm going to save it for the next video because it's a little bit longer example, and this video has run a bit longer than I wanted it to. So just make sure that you do these first, though, and you get the setups, and you understand why. For these last couple problems, we just needed Q, where for the calorimeter problem, we needed a minus Q lost equals Q gained. And then make sure you can follow the mathematics and you understand each and every step, okay? So the next video, we'll do one more heat exchange example.